Today we are going to consider binding energy, the definition and the calculation, and then mass defect, its definition and its calculation, and binding energy per nucleon. What is the meaning of binding energy? It is simply the energy required to separate the nucleons of an atom. The energy required to separate the nucleons of an atom. You can also define it as the energy that must be added to the nucleus to break it apart into separate neutrons and protons. So the energy that must be added to the nucleus to break it apart into separate neutrons and protons is what is referred to as binding energy. Let me give you a very brief illustration. Let us assume that this is our helium nucleus. And it has mass number 4, proton number 2. So from there, we can estimate the neutron number to be 2. So here we have 2 protons and 2 neutrons. And then the actual mass is M1. Now, we require to separate these protons and the neutrons, which will require some amount of energy. And at the end of the process, we have been able to separate the protons and the neutrons. Now, if we estimate the mass, masses here, look at, we have 2 protons here, so this is 2p, plus we have 2 neutrons here, so this is 2n. And then if we substitute the value of proton given into p and the value of the mass of neutron given into n, it will give us a single value. So the value of M2, the calculated value of M2, when we subtract with M1, we will discover that they are not the same. So the differences in masses change in M, which is M2 minus M1. The differences in masses is what gives us what they mean by mass defect. So what is this mass defect? It is the difference between the actual atomic mass, the difference between the actual atomic mass and the predicted mass. The difference between the actual atomic mass and the predicted mass. Now, remember, we were talking about energy, binding energy. So binding energy, EB, is change in mc square. So now, the binding energy, for us to get the binding energy, we have to multiply the mass defect by the speed of light, the square of the speed of light. That is to say that we are going to convert the mass defect to energy. So that amount of energy, that minimum amount of energy that is required to separate the protons and the neutrons in that atom is what is referred to as binding energy. Okay, so that, I think I have been able to explain that second definition. Binding energy is that energy that must be added to the nucleus to break it apart into separate neutrons and protons. Let us go back to our problem so we can. Okay, so binding energy, that energy that must be added to the nucleus to break it apart into separate neutron and proton. Let's look at these examples. This one says, consider the helium nucleus. Find the mass defect, the binding energy per nucleon, given that the proton is 1.0076 U, neutron 1.009 U, and the mass number of helium is 4.0028. So these values have been given, and we are to estimate the mass defect, binding energy, and binding energy per nucleon. So we are going to calculate the mass defect, and for us to be able to get that, we have to find the value for the neutron, and the proton is given, the mass of proton is given, mass of neutron is given, mass of helium is given. In the equation, helium nucleus is considered. We have proton number here, we have mass number. So we are going to first find the neutron number. Remember that A equals to Z plus P. And Z is the proton number, Z plus N. Z is the proton number and N is the neutron number and A is the mass number. So our Z here in this case is 2. So our A here is 4. So what I'm going to do is, if we are to make N the subject, so we'll now have N equals to, that's the neutron, equals to A minus Z, which is 4 minus 2 equals to 2. So we have also estimated the neutron number to be 2. So we have our mass number to be 4, our proton number to be 2, and our neutron number to be 2. Fine. Remember, A equals to Z plus N. A equals to Z plus N. Z is the proton number, N is the neutron number. How many proton do we have? In this case, we have 2. So I'm going to put 2 here. A equals to 2 times, or 2 into the mass of Z. Anyway, let me just make it this way. 2 times Z plus, then our neutron number is 2, so 2 times N. Okay, so we have that this will be 2 times, what is our Z? The proton number that was given, the mass of the proton number that was given, 1.0076 U. 2 times 1.00 76U plus 2 times the mass of the neutron given 1.009U. 1.009U. By the time you simplify this value, it will give you 4.0332U. 4.0332U. Okay, so this is the predicted mass. Now, we want to calculate the mass defect. So this is our predicted mass here. We want to calculate the mass defect. So mass defect would be change in M equals to this predicted mass 4.0332U minus the actual mass, which was given, mass number of helium. Look at it here, 4.0028U. 4.0028U. Okay, so we will end up having M equals to, when you subtract the calculated mass by the actual mass, you have 0.0304U. 0.0304U. Okay. All right. So this is our mass defect. This is our mass defect. Okay. Now, the next question said we should find the binding energy. Okay, so I find the binding energy. Binding energy is simply converting this mass defect into energy. Remember that binding energy EB equals to mc squared. Okay, but in this case, our mass is 0.0304 and the U here is a unit of mass. So by the time we convert this to milli-electron volt, it gives us the value of the binding energy. So binding energy EB equals to M, change in M, which is 0.0304. 0.0304 times U. And what is this U? U is estimated to be 931 milli-electron volt. So in place of this, we are going to substitute 931 milli-electron volts. So we will now have 931 MeV. Multiply these two. What do you have? What do you get? EB equals to what I'm seeing here is 28.3024 milli-electron volts. You can also try it and see 28.3024 milli-electron volts. Okay, the next question was binding energy per nucleon. So the binding energy that we have gotten here, which is 28, is the energy needed to overcome the attractive nuclear force between the proton and the neutron in the helium. So this is the energy, the minimum amount of energy that we would be required to separate the proton from the neutron. And if we are to find the binding energy per nucleon, that would simply be the value of the binding energy EB all over the mass number. What is the mass number? The mass number is, we were considering helium. Look at the mass number here, 4. So this would be the value of the binding energy, 28.3024. 28.3024 divided by A, which is 4. That will give us 7.07 milli-electron volts. And this value tells us about the stability of that atom, the stability of that nucleus. Okay, let's go back to the question. So we are through with example 1. We also have other examples here, example 2 and example 3. You are still going to use the same method to solve them. So I'm not going to solve this one. I would allow you to attempt it. Then we look at the result. Maybe I will solve it in our next class, but I would like you to solve it and you let me know so we understand whether you really get what I'm trying to say. Example 2 says the strongest bond nuclide is this Ni 62 and 28. Its atomic mass is 61.928349 U. Find the mass defect. Find the total binding energy per nucleon. Take the mass of proton as 1.0073 U. Mass of neutron as 1.0087 U. Then this example 3 says the nucleus of the deuterium atom, called the deuterium, consists of a proton and a neutron. Calculate the deuterium's binding energy in milli-electron volt. Take the atomic mass of deuterium to be 2.014102 U and proton 1.0078 U and mass of neutron 1.0087 U. Okay, so I think with this we have come to the end of today's class.